present new map problem 7. So we shall check how good are we in knowledge of trigonometric functions. Can we calculate with them? Here is one pretty heavy expression. So we shall, it's not obvious on first sight, even to me, how to prove this equality, which should be valid for arbitrary real numbers x, y, and z. So good luck, and we shall now solve the previous one, the problem 6. Here we have only 2 line segments, but already we have pretty interesting mathematics given here. So we shall see that it is not completely easy at all. Let me start with this. I shall present 2 solutions. First one will be analytic solution, which will be more lengthy but more approachable to wider audience. And later, inspired by this solution, we shall give a constructive proof, which will be much shorter, but maybe harder to follow. In the first approach, we shall take a coordinate system. Should take a coordinate system in such a way that one line segment lies on one axis, for example this horizontal axis, so this will be a line segment AB. And we also choose coordinate system in such a way that the intersection point of 2 line segments is actually in the origin of the coordinate system, so here will be intersection point I. And so the other line segments simply passes through I, and so this is the second line segment with points C, with endpoints C and D. So we can always choose coordinate system in such a way that we make our calculations easier, and it seems to me that this is optimal for this problem here. So the coordinates of point A will be, I will denote it as minus A, comma 0. So the second coordinate is of course 0, but I choose first one to be minus A in such a way that A will be greater than 0 actually. I could I can do this also without this minus sign, but somehow I prefer this here. So the point B will be B0, and this line segment CD actually lies on one line through the origin, and the equation for such a line is y equal to some coefficient k times x. So x and y are simply coordinates, our x and y. So we know that if for example, first coordinate of point D is, let it denote to be D, then the second one is also k times D. because it lies on this line. So we shall denote also C also with a minus I in this notation, like minus C times comma, and the second coordinate is minus K times C. Okay. In this way, A, B, C, D are all greater than 0, and K is actually any real number. In this way, on my picture, K is negative because our linear function for C and D is decreasing. If it is increasing, it is positive. We shall see that actually the problem is not well defined. This K is equal to 0, because then two line segments overlap, not just in one point, and in that case the problem is not well defined. Actually, K will be different from 0. So the problem is to choose, okay, let me maybe change the color for the time being. We shall choose one point here, first line segment M, and the second one on the line segment CD, N, in such a way that the distance AM, this one is equal to the distance CN. So these two red distances should be equal, and we want to minimize this segment MN. Okay. So I should change color again. M is also on the coordinate on the x coordinate. So coordinates are M, 0. Again, second coordinate is 0, and N has coordinates N, and the second one is again K times N, because following this equation on the lines CD. So what we know about those coordinates, that M is actually between minus A and B, because M is on line segment in between A and B, and because N is between C and D, also we know that N is between minus C and D. We can notice that our problem is completely independent on points B and D. Points B and D doesn't matter. We can change B to be something like here, or change D to be something like here, and the solution will be the same. So our solution will not depend at all on coordinate B and on coordinate D. Those 2 points are irrelevant for our problem, because we only check the distances from A and C here. So we expect our solutions to depend actually on A, C, and K. We will obtain our solution to depend on those 3 numbers, A, C, and K. Okay, we start. First we have that AM is equal to Cn. AM is simply M minus A. We simply take the difference between x coordinates of point M and A here. For Cn, we need to calculate by Pythagorean theorem here. So the distance between x coordinates of those 2 points are actually n minus c, but because of the Pythagorean theorem, we also obtain square root of 1 plus k squared. So let me briefly explain here. Actually, this one line segment is actually what I denoted here, and this will be n plus c, and this second one is also n plus c but times k, and by Pythagorean theorem this is what we need, is given here. This is m plus a, and we don't need absolute value because of this condition. Actually here this will be positive, and also on the right side we have n plus c times square root of 1 plus k squared. Okay, we shall need this condition later. This condition should always be satisfied. So we need to minimize distance from M to N. Simply we shall take square of that distance, because Mn and Mn squared are simultaneously have minimums in the same point, because quadratic function is increasing on positive numbers. So we can take without loss of generality Mn squared here, and Mn squared is actually also by Pythagorean theorem. We take difference between x coordinates m minus m squared, plus we take difference of y coordinates, which are simply k times n minus 0. So I'm using actually these coordinates here for m and n, and the well-known formula for the distance of 2 points. But without a square here, we will need to take square root on the right side, and it will be it is more convenient to calculate this way. So we need to take this to minimum. Okay, let me write this once more in simpler way, so we don't miss this minus 0 and square this k squared and squared. So this we can now check that this is actually a function of two variables, m and n, which we need to minimize. And we have this condition. Those of you who are familiar with minimization with constraint, you can use Lagrange function with Lagrange multiplier, but we shall of course solve this in much simpler way. So we shall express m from this constraint here. Simply we shall put a to the other side here. M is so n plus c times square root of 1 plus k squared minus a, and then we shall substitute this instead of m here. So we obtain that mn squared is actually n plus c square root of 1 plus k squared minus a, this is for m, then minus n and all squared, and plus k squared n squared. This will be now simple minimization of function of one variable. This will be function f of variable n, and we can simply minimize this. Of course, the candidate is the 0 point of the derivative of that function, but we shall see that we even don't need derivatives here. This will be actually a quadratic function of a variable n. It's not completely obvious at first point because it is a pretty much heavy expression, but f of n is, we shall now calculate, I shall now use the famous formula for square of binomial. So I shall take this like binomial of two terms here. So we will obtain n plus c squared times 1 plus k squared. Then we will obtain term minus 2 a plus n plus c square root of 1 plus k squared. So this is simply by formula, this first term times second and times 2, and plus the second one squared, which will be a plus n squared, and also finally the last one is this one, k squared n squared. So we shall actually now show that this can be written as some coefficient a times n squared plus some coefficient b times n and plus some coefficient c, like a quadratic function with a being negative, and we know that the graph of such actually a will be positive, not negative, and the graph of such function is a parabola, and we actually know where the minimum of parabola lies, and we actually have a simple formula for the x coordinate here, actually n. So the minimum will be obtained when n is equal to minus b over 2a. So this is the famous formula for the where the minimum of quadratic function lies. So we see that we simply need to write down what is a and what is b here. A is the coefficient in front of n squared, and n squared will be obtained here. Here we have n and will be square here. So the first term will be actually 1 plus k squared in front of n squared from this first term here. Then n squared will be obtained also in this here in the second term when we multiply n times n, and the coefficient will be this minus 2 together with this square root here. So also we have minus 2 times square root of 1 plus k squared in front of n squared. Also n squared will be obtained here when we square this expression. So here we obtain simply 1. And also in the last one we have coefficient k squared in front of n squared. So this is it. We can sum these two equal terms, and we can put 2 in front of the parenthesis, and we obtain simply 1 plus k squared minus square root of that same expression. Actually we now see that this is always greater or equal to 0 because this term 1 is greater or equal to 1, and the square root of such a number is not bigger, so this will be non-negative. And actually to obtain strictly positive here, to obtain well-posedness, to obtain a problem which indeed has a minimum at one point, we actually need what I announced earlier, k greater k different from 0. And this is just the fact that two line segments at the beginning intersect in just one point. They do not overlap in more points. So this is actually a natural assumption here. This is what we expect. And now I need also to calculate b. B is in front of n, so n will be obtained here in the first term. Okay, I will now change color again, that this will be easier to follow. In this quadratic of binomial, we have n as 2n times c, so we will obtain 2c, but also multiply this with term with k multiplied with 1 plus k squared. Okay. And then in this second term we obtain n as a times n and c times n. So we will have this minus 2 in front. We will obtain here a plus c in front of n, and also times this square root 1 plus k squared. And also n will be the middle term in this square of binomial, 2an, so plus 2a in front of n. Okay, so this is it. We can write this as we can write this as okay, so far like this. And now I will use this formula here for the minimum, for the n for which we obtain minimum. As we said, n will be minus b over 2a. And so this will be just in numerator the negative of b, which I shall write in a more convenient way. I shall write as 2a plus c. So I'm starting with the opposite of this term. So I will have square root 1 plus k squared. And also I can have this 2a plus c here and here. So I can actually take minus 1 here. And the left, what we have left here, we have minus 2c times k squared. The negative of this 2c times this k squared. Okay, and in the denominator we have 2a, this is a, so times 2 we have 4 in front, so 4 times 1 plus k squared minus square root of 1 plus k squared. Okay, I'm going to change the color once again, so we can cancel this 2 and this 2 with this 4. We have 2 here, and actually okay, I actually need a more convenient form for denominator to obtain a simpler expression to cancel even more. Okay, I didn't see this before, so I shall write separately what I have in front of a, and in front what I have as a coefficient with a. A is here, so I multiply a with this bracket here, so with square root of 1 plus k squared minus 1, and I multiply c also with this bracket, but also with minus k squared in this last term. So I will have square root of 1 plus k squared minus 1 and minus k squared. And in denominator I have 2 times 1 plus k squared minus square root of 1 plus k squared. And now I can actually write this as 1, as 2. Actually I can take one factor out. I can take a square root of 1 plus k squared in front of parentheses. So I from this another square root is left, and from this only minus 1. And in numerator a times square root minus 1 will be left, And in this second part in front of c, we again take the square root in front of parenthesis and obtain 1 minus square root of 1 plus k squared. So now we have a nice cancellation actually here. Let me change the color once again. So we will be able to cancel this with this and with this with minus 1 left. So I will write here the formula. Okay, actually, okay, maybe, yes, this will not be good place. I need to take some space for my video. Okay, never mind. So I can write here in the next corner we obtain actually that n is equal a minus c times square root of 1 plus k squared in numerator, and in denominator we obtained 2 times square of 1 plus k squared. This is what we obtain for n. And now, if we substitute this here down in this formula, we can obtain m also. I shall skip this calculation, it's not so difficult now when we cancelled this expression for n. It's not that difficult for m. We obtain even simpler formula. For m we obtain c times square root of 1 plus k squared minus a over just 2. Okay, and now when we obtained this formula for m, and when we erased some free space here, we shall give an explanation and idea for the constructive proof of this problem. Namely, let me draw this once again. So if this is A, and if this is intersect point I, and if this is C, actually minus A is the length of this segment. This line segment actually is minus A. Let me recall that A was sorry. Actually, no. The length of this is A, but the coordinate of A point is minus A, and this length is A. A was positive, and the length of this segment is actually C because this point had coordinates minus c and minus k times c, and again by Pythagorean theorem this length is c times 1 plus k squared. So if we transfer this segment here, that this point should have coordinates c times square root of 1 plus k squared and comma 0. So in the way that this line segment is equal to this one, this line segment here, we actually can interpret this formula for m to be a midpoint between this a and this point, let me call this as point E, for example. So A has x coordinate minus A, and E has x coordinate c times the square root, and the midpoint of these two will be somewhere here, and the midpoint will have the coordinate which is actually arithmetic mean between these two, minus a plus c times square root over 2 arithmetic mean of those two coordinates will be the coordinate of this midpoint here. And this is exactly what we obtained for m. This is exactly our solution m. So the constructive proof is simply to transfer this line segment ci here on the right on the x coordinate, and then obtain this point E, and then simply take the midpoint between A and E. So here we need to choose our point M, and N will be somewhere here, and this is the minimum in this case. So this was now easier to construct when we know this formula which we obtained for M. But how can we maybe conclude this without knowing the formula? This is probably the hardest to conclude, but let me describe this also once again. So I shall again draw this. So here we have A, here we have C. Okay, and if we start with point M here and with point N here, we will have this length here. And then we approach with N here to the intersection point, and with M also here in the intersection point by the same amount. And we will actually decrease this distance until we reach intersect point with one of those points. Here Cn is smaller, so we will reach with N here, and with M m here. And we will obtain this. If we continue with this, at some point we will get with m here to the intersect point, so this will be m prime, and n will go here. This will be n prime. And we will again obtain the same, distance. And if we continue with going with n here and with m here, we will again increase the distance. So the minimum should be somewhere between those two cases, between this mn case and between this m prime n prime case. I shall draw this once again, but now only with those cases. So let me draw this bigger. Let m be here and n be here and m prime be here and n prime be here. So one extreme case is if m is here and m is here, and another one if we got with m here to m prime and with n here to n prime. So in both cases the distance between m and n is actually this, let me call this x. This is x, and also this is x. And if we take m somewhere in between, and we will see that the minimum is actually in the middle point here, then n will go here also to the middle point, but let it be two arbitrary points in such a way that this distance here is equal to this distance here. So now the distance between our points will be this one. Actually, we want now to minimize this distance. But now we are actually in the beginning of our problem, but we now have two segments. I shall draw this in blue. We have one special case here. Our line segments now are this one and this one. Maybe to draw this again here. We reduced our problem to the special case where two segments line connect in one point. So let now this be like A and B and the beginning, and C, D in the beginning of our problem. But now they have just one endpoint in common, and they are on the same length, x here and x here. And now we want to find the point we want to find the point here and the point here in such a way that the distance here is y and the same distance y is here, and that this is minimum. And now we can simply calculate that distance by noticing one another triangle with right square, right triangle, and to apply a Pythagorean theorem again. Namely, if we denote this angle with phi, what we have here, that this length is actually consists of two parts. This one, which is x minus y, and plus this second part here, which is actually orthogonal projection of y, so it is actually y times cosine phi. And this second side of this triangle is actually y times sine of pi. And if this is our point M and our point M, by Pythagorean theorem, mn squared is actually x minus y plus y times cosine phi squared plus y times sine of pi squared. And I shall now skip this part. This is now much easier to minimize than before. We again obtain quadratic function as before, but now we obtain that the minimum is just at y equal to x over 2, so that the minimum is in the midpoint here between A and B. In this way, we again need to calculate as something, but it's much easier to conclude that the minimum is actually the midpoint between A and E as described earlier. Okay, I hope that you enjoy, that you find something interesting for you and to improve your mathematics ability. Thank you very much for watching.